Training an image classifier from scratch requires massive datasets, perfectly balanced categories, and often days of expensive compute time just to get off the ground. Transfer learning bypasses this computational bottleneck entirely. Instead of starting with an empty network, we start with a model that already knows how to see. We start with ResNet-18. Trained on the massive ImageNet dataset, it's already an expert at recognizing universal patterns and textures. Every input travels through feature extraction layers, identifying core visual elements. Then, that data passes to the final classification layer. To execute this pipeline, you simply need a standard PyTorch environment. Starting with a pre-trained foundation turns a multi-day training cycle into a high-performance model that's ready in minutes. Step 1. Load ResNet-18 and freeze its feature extractor to preserve pre-trained weights. Setting requires grad to false locks these in place, preventing optimizer updates. Step 2. Replace the final output layer. We remove the original ImageNet classification head and attach a blank linear layer tailored to our custom classes. Freezing the convolutional base and swapping out that final classification head provides the mechanical foundation for almost all transfer learning pipelines. Let's test this setup using the cat-dog-panda dataset. After downloading the images, we apply standard pre-processing transforms to resize and normalize the data so it matches the format ResNet expects. This line chart shows validation accuracy during training. Because ResNet-18 already understands animal shapes and standard photography, it adapts instantly. The model achieves 98% accuracy in just 3 epochs, with 0 additional data augmentation. When we run inference on the test set, the results back up the chart. The network correctly identifies these animals with confidence scores consistently hitting 0.99 and a perfect 1.0. But a 98% accuracy rate leaves a small margin of error. Looking at the incorrect predictions, ambiguous angles, weird lighting, or partial occlusions will still occasionally trick the system. This first dataset succeeded rapidly because the new animal images are a natural visual match for the general internet imagery the model encountered during its original training. Now, let's run this exact PyTorch pipeline on a different problem, the American Sign Language dataset. Unlike pets in natural environments, these show specific hand positions, intricate joints, and flat backgrounds. This plot tracks validation accuracy on the ASL data. The trajectory is completely different. The network is severely struggling. Even after grinding through 100 epochs, accuracy plateaus around 87%, compared to the effortless 3-epoch victory with the animals. This performance gap illustrates domain shift. The original ImageNet dataset maps smoothly to the cat-dog-panda images because they share similar visual qualities. But mapping general images to highly specific ASL hand signs crosses a wide visual gap. A pre-trained feature extractor is ultimately bounded by the visual similarity between its past experience and its current task. You now have a fully functional PyTorch workflow. You can take a pre-trained model, lock its layers, swap the classification head, and benchmark its performance across entirely different datasets. But to break past that 87% ceiling on the ASL dataset, we have to rethink our constraints. Strictly locking the entire feature extractor prevents the model from adapting to radically new shapes. The next step is fine-tuning. By intentionally unfreezing the deepest convolutional layers of the ResNet, we allow the network to adjust its core feature recognition, giving it the flexibility to push that ASL accuracy past 90. Reusing a model provides the foundation, but adapting it to specialized data depends on knowing when to unlock those foundational layers for further training.